So this talk, I'm sorry, my name is Adam Smith. I work at Penn State. I'm on sabbatical this year in Boston at VU mostly. And I'll be speaking about I'll be speaking about forward stability, privacy, and online learning. This is based largely on a paper I wrote with Aberdeep that appeared at NIPS just a few days ago, but also based on conversations with a number of people, including Aberdeep and Pratik. Okay, so we've seen various, connections along these lines, in particular in Aberdeep's talk earlier this afternoon, but in general at this workshop. And so I'd like to look at a particular connection between privacy and online learning, and the notion of stability that seems to be most relevant there, which is sort of something called forward stability. A lot of what I'm going to say is sort of stuff that is, I guess, implicit in most cases in the online learning, the non-private online learning literature. But I'd like to give you kind of my way of thinking of it, my take on it, and hopefully this will, give you some insight into how this set of algorithms works. All right. So what's the problem we're looking at? Imagine we've got some learning problem. So we've got two sets, X and C. We think of X as where the data lives, and C as the parameter space that you're trying to learn something in, and some loss function that takes a pair of things and gives me a real number. And you've got this setting where you've got this algorithm who's trying to learn, and this environment that's trying to put obstacles in the algorithm's way. And here's what happens. We play this game for several rounds, where at each round, the algorithm announces, well, here's what I think the parameter vector should be. Here's what I think is going, this is my current model of the world. The environment says, well, here's some data. And the algorithm pays, and it pays the loss of this prediction on the data that was presented. And, whoa, not my laptop.
I don't know. It keeps wanting to do this. You can just disconnect it.
Yes, I can. All right. So we'll think of the data. So the data, what the data is can vary from application to application, but we'll sort of think of the data as actually giving me a function, as a cost function. Okay. So normally we think of data as strings and stuff like that, but let's just think of it as the adversary, the environment produces a cost function. So this is just the loss function with the data fixed. And so what I pay is sort of, first I make a prediction, then I see the cost function, and I pay this cost function applied to my prediction. Okay. So this seems like a very difficult model for the algorithm to live in, because it has to make a prediction for, it pays for something that it hasn't yet seen. And the environment in full generality can choose this FFT based on the prediction that was made. But the way we'll sort of make the algorithm's life easier is that we're only interested in minimizing the algorithms with regret with respect to the best fixed choice in hindsight. Okay, so the regret is the costs I paid minus the best single parameter I could have played with the whole time. This is one notion of regret. There are several others. This is the most prevalent one. No? I can only go backwards. Okay, so we'll start at the last slide of the talk. Okay. So most of the online learning problems I'm going to talk about, in fact, I'll only mention one non-convex problem, and I won't even get into any details. But essentially, I'm going to be talking about convex learning problems, where so both the set C of available parameter choices and the functions that are the cost functions that I'm playing against, these are convex. Okay, so an example would be learning from experts, which came up in John's talk this morning. Here I imagine my W is a distribution over experts. Okay, so either the name of one expert or maybe some convex combination thereof. And X is sort of the cost, the money lost by each of my possible investment advisors. and what I lose is the sort of the inner product of these two things, right? The money lost by the investment advisor I chose at this time. Least squares regression fits into this. Median problems type problems fit into this framework. There are lots of things that are convex. I don't think I have to belabor that point. So, what are the kinds of algorithms people use to solve this? There's a large literature on that, but let me give you two different looking things that come up a lot. One is gradient descent. So there you're given at each time step you're given the cost function, and you pay your cost, and then you want to update based on the cost function you just saw. And so what you do is you take your gradient at the current parameter value, and you update it. You add some multiple of that to your current parameter. So you sort of take a little step as if playing gradient descent, but with respect to the cost function you just saw. And if necessary, you project yourself back into the set that you're allowed to play. A very different type of algorithm is something called follow the perturbed leader. So this is something that is specific to learning with experts, at least as I'll state it. So here, again, my convex set is the set of distributions over the labels of the experts, of which there are D. My cost functions are linear because it's I'm paying for the inner product between W and F. So at each time step, again, I receive a sequence of numbers between 0 and 1. I pay what I have to pay. And then the way I do my update is I'm going to define a distribution. I'm going to define this random variable, vector-valued random variable. I'm going to add up all the cost vectors I've seen so far. I'll add random noise to each of those things. And I'll pick the one that has the minimal noisy cost. Okay, so this is, I'm intentionally phrasing this algorithm in a way that makes it look like basically the exponential mechanism, or the simple easy to implement version of the exponential mechanism. And this is this is follow the perturbed leader, or one of the versions of it. I believe this version was proposed by Kalai and Vampala, but don't take me too seriously when it comes to references in the online learning literature. Yeah. So these are two prototypical types of algorithms. A lot of the algorithms that are actually used sort of smell like one of these two. All right. Okay, so what about privacy? So what we're going to do in this talk, I'm just going to look at designing. I'm not going to look at the kind of more sophisticated type of transformation that John was talking about this morning. Here we're just looking at designing differentially private, designing online learning algorithms that are differentially private. Right? So I'm going to think of the data at each step as belonging to some person. And what I want is that essentially what I want is that the entire vector of outputs of my algorithm be differentially private. The entire, not vector, but list of parameter vectors be differentially private. So this corresponds to what Dwork-Noer, Patasi, and Rothblum called event-level differential privacy under continual observation. We think of an adversary as picking two adjacent input streams, x and x prime. They differ in one data point or one cost function. And then I'm going to look at the distribution on the two output streams, and I'm going to require that those distributions be epsilon delta close. Okay. In fact, this is not quite the definition you need. What you really need is an adaptive version of the definition where the adversary can sort of choose the stream online based on the things you've said so far. And it turns out those definitions are slightly different, but not in ways that matter for today. Okay? And just one useful thing to know is that there's one algorithm for this model, this model up here, that it's actually private in both models, and that comes up a lot in these sort of continual observation settings, and we're going to use it too. So basically, it's an algorithm for evaluating prefix sums. So imagine that I've got the input is a stream of vectors, real vectors, and I want to approximate all the partial sums. Then what I get is basically there's some binary tree-based algorithm that gives me a pretty good approximation to each of the sums, and with a sort of a polylog error and a dependency on the dimension that's missing. So this should be the diameter times the dimension. Yeah. Well, okay. So the L1 error, it doesn't really matter here. The L1 error scales logarithmically or polylogarithmically with t, and there's another term of the dimension that I omitted. Okay. But this algorithm is epsilon differentially private in both models. Okay. So this is our notion of privacy. So we want to design now online learning algorithms that satisfy this notion of privacy. So how hard is it to do this? Right? So some algorithms actually just kind of look naturally differentially private. So this follow the perturbed leader that I defined 2 slides ago, as I said, you can think of it as basically implementing the exponential mechanism. And so it does give you some kind of privacy, at least if I just look at one output at a time rather than the entire vector of outputs. Okay. And so there's still some thinking that goes in there. On the other hand, some algorithms are much harder to analyze. For example, this gradient descent algorithm, it's not quite as obvious how you should think about it in terms of privacy because, the choices I make early on in the algorithm have some weird effect for the rest of time. And so it's not entirely clear how you bound the effect of one term on everything that comes later. Okay, so what I'll try to do in this talk is to give you some algorithms for private online learning, and I'll try and highlight the connection to stability. And so this is sort of an outline. I'll talk about forward stability and a sort of regret in this kind of modified model where I got to see the future. We'll call this the crystal ball regret. And then so we'll sort of set up a framework for analyzing these algorithms, then look at a couple different ways of sort of filling in the blanks in that framework. And just a few notes. There are almost no citations in this talk to the ideas we're using from the online learning literature, so that's unfair, but I realized that I didn't have time to do the research to put exactly the right citations in, and I don't want to be wrong. And the other note I'll just make is that John Ducci, what's the correct way to pronounce your last name? Ducci. Will give a talk tomorrow on results that have a similar flavor for what's called the local model, and we'll hear about that tomorrow. Okay, so what do we know about what are the results that are known on differentially private online learning? Well, for the prediction from experts problem, you can get a couple of different results depending on how you kind of use this basic follow the perturbed leader algorithm. One of them is from Duda, Dork, Noor, Patasi, and Rothblum, and the other, in fact, an observation one can show, and this is due to conversations with Abradeep, is that in fact the original Kalaya and Vaipala algorithm already gives you some non-trivial, if you just set the parameters correctly, already gives you a non-trivial differentially private learning algorithm with a good dependency on the dimension D, better dependency on the dimension D. One can get algorithms for convex functions, for general convex functions under a smoothness condition, assuming they're Lipschitz, get something like square root of t, d times square root of t dependency. If you assume these functions are strongly convex, you get much better types of guarantees, something like logarithmic. And a recent result is that you can also get an online approximation for a very non-convex problem, which is finding singular, rank k approximation of the right singular vector space with again some dependency that's something like square root of t times some small polynomial in the dimension, and that's work due to Dork, Talwar, Thakurta, and Zhang that I guess we'll hear some more about tomorrow or Saturday. Oh, and one thing I'll mention is these are all in a sort of worst case model. As I said, this kind of adversarial model. It turns out you can get much better analyses if you're making stochastic assumptions, and I'm not going to talk about that. Okay. There's a variant of this basic model that I've described, which is called the Bandit setting, or the partial information setting, where the algorithm doesn't actually learn the full cost function at each phase. What it learns is only the cost that it paid. right? So if you don't go to the other investment advisors and you don't go, work with them, then you don't know how much return you would have gotten on your investment with them, right? You only learn the money you actually lost. And it turns out that setting is very different. You can read about it in the paper. I'm not going to talk about it more. So we're going to stick to the full information setting because it's much simpler, and basically all the ideas I'm going to discuss, those are the ideas that we can use in the Bandit setting. The main ideas are the same. There, sorry. Okay, so this is again the talk outline. So let's talk about forward stability and our little crystal ball. Okay, so just some background. There's this, one thing you might want to do is called follow the leader. And in fact, it's surprisingly, it's not a terrible idea. So follow the leader says, I look at everything I've seen in the past, all my cost functions that I've seen so far, and I'm just going to make, at each step, I'm just going to play the strategy that would have served me best in hindsight. Okay. So in general, this is actually an awful idea, right? And that's because you're sort of always fighting the last war, right? So this algorithm can be made to kind of thrash around in horrible ways, and if you set up your input adversarially, then this can have very high regret, omega of n. But it's nonetheless, it's still the basis of most of the online learning algorithms that are out there, and you might wonder why. And the sort of counterintuitive answer is that actually, follow the leader would be a great idea if hindsight included a little bit of the future, right? If you could actually sort of see what's coming up next and make your decision against knowing the cost you'll actually be paying. So let's just consider for a while a slightly different model. So here's our original model where we pay for I make a prediction, I see a cost function, and I pay. Okay, so let's imagine a different model where I see a cost function, I make a prediction, and then I pay, right? And I pay for the previous times. I pay for the previous cost function, not the next one. Okay, so we'd all love to live in this world, right? I certainly would. I've occasionally had cause to regret decisions, but somewhat surprisingly, it's actually useful to imagine living in this world and think about things this way. So let's call the crystal ball regret, also called the forward regret. Let's call that the cost I'd pay in this sort of crystal ball model where I get to see the future, minus, as before, the best choice I would make in hindsight over the entire run of the algorithm. Okay. So the beginning observation is that the basic follow the leader algorithm actually has crystal ball regret that's at most 0, right? Like I'll never actually regret my decisions in that model. Okay, and maybe that's not surprising. It's because I get to see the future. Okay, but how can we use that? Well, suppose I have this promise that somehow my parameter predictions. Suppose I have a promise that I've got an algorithm that A has low crystal ball regret, and furthermore, the predictions I make at each time step don't change too quickly. Okay, so if the predictions I make at each time step don't change too quickly, then in fact my true regret really is close to this crystal ball regret, right? And so this motivates us to let's sort of formulate another condition, which we'll call stability. And stability is just, the sum over all time steps of the difference between the cost I pay in the crystal ball model and the cost I pay in real life, right? And the idea is if each of these pairs is close, then each of these terms will be small, and maybe that'll buy me something. Okay, this forward stability is also called online stability, I guess, or some variations on this are called online stability. There are a number of variants of this definition out there. Okay, and then the useful fact, which is sort of obvious from the definitions, is that the regret is equal to the forward stability plus the regret in the crystal ball model, and so I just want to bound each of these two. All right, so that gives us a basic a basic setup, and we're going to, and again, there's nothing new here. So pretty much this is the way that online learning algorithms are designed in the sort of non-private setting, or at least the way they're analyzed. And but we're going to try to use this way of thinking about it to get differentially private algorithms. Okay. All right, so we need two things. We need to bound this sort of crystal ball regret, and we need to bound our forward stability. So to bound forward stability, we need, as I said, to show that the cost I pay when I see the future is sort of the same, roughly, as the cost I pay when I, in real life. And we'll see. So there are really like two very different ways to actually approach this. Okay. So one is to use sort of statistical closeness. Okay, to look for W and WT plus 1 that are somehow close in distribution. So suppose I just go and design a differentially private algorithm, right? And then I hope it has good online regret. Well, what I know is if the algorithm that produces WT, that produces each of my outputs, if it is itself differentially private, epsilon t differentially private, then the distributions on WT and WT plus 1 are epsilon t close. And so the stability of the algorithm, the sort of difference between real life and the crystal ball model, is at most the sum of these epsilons, times something which is like the maximum, you have to scale it according to how big your costs can be, right? So the maximum cost you could have paid on any one, at any one time step. Okay, and this is just like a statistical distance argument. So this isn't exactly the sum of the epsilons. It's like e to the epsilon minus 1. Alternatively, you could go via closeness in norm. Okay, so rather than asking the distributions on WT and WT plus 1 to be close, you might just ask that they be actually like close as vectors, right? And the second, so the way these analyses proceed is that I'll assume, I'll hope or ensure somehow that my individual cost functions are not merely convex, but strongly convex, meaning they have some real curvature with respect to some norm. And then I can ensure that norm of WT minus WT plus 1 is small. And then as long as my functions are also smooth, meaning they don't change too quickly, then the stability I get is roughly going to be the sum of the distances bounded above by the sum of the distances from WT to WT plus 1. And as long as that sum is not too problematically large, then I'm in good shape, right? So this sort of tells me, this kind of analysis tells me how much does my parameter vector wander around, what's the total distance it traveled over the course of the algorithm, right? And so what it says, if you think really slowly, in fact, maybe just making the best prediction in hindsight isn't a bad thing, because you're pretty much going to be competitive with the future. All right. And then, so this doesn't talk about privacy, but it tells us that we already have some sort of stability property built in, and then we can sort of also get differential privacy if we're careful. And then, so that tells us how to, but these are sort of the basic ways to think about forward stability, and to bound the kind of crystal ball regret. It turns out you use the same idea in all of these cases, and what you do is you think about your algorithm's not actually running follow the leader in general, but what you try to argue is that it's actually running follow the leader with respect to some other sequence of cost functions, not your true cost functions, but something else. And that other sequence of cost functions is somehow close enough to the things you were after that the crystal ball regret is small. So this is this is kind of as I said, the generic blueprint in its two variants that are out there. And for the time I have left, I guess I'd which is not much, I'll tell you a bit more about each of those. How much time do I have? Another.
I think you should take another 5 minutes.
5 minutes. All right. Okay, so that was just my outline again. So let's just talk about strong convexity. So a function is Lipschitz with respect to some norm if the difference in the function is bounded by L times the norm of the norm of the difference between the arguments. And that's a very natural definition. Strong convexity, maybe slightly less standard, is if I can I can think I can think of convexity as giving me convexity is the statement that a given function can be bounded below by if I've got some function, I can take any point and I draw the tangent to that point, and that gives me a lower bound on the function. That's the definition of convexity. So strong convexity is the condition that I can bound it by a quadratic function, okay, with some non-zero curvature, and sigma is the the parameter of the strong convexity is how curved that quadratic is. Okay, and a basic lemma is that if f is sigma, if I've got some function that's sigma strongly convex, and some little function, little f that's L Lipschitz, and I look at the two minimizers, one for big F and one for big F plus little f, then those two minimizers are going to be close. Okay, and they're off by at most L over sigma. So this lemma comes up. I made up the name convex stability lemma. It comes up all the time. I don't think it normally gets a name. Okay, so why is that lemma useful? Well, suppose that I've got a bunch of cost functions that are all strongly convex. Okay. Then I will use this stability lemma to argue that in fact the follow the leader has low regret. Okay, and so that gives us a low regret. It's a standard way to get a low regret algorithm. The problem is that just sort of adding privacy to follow the leader directly doesn't work very well. It costs us a lot in accuracy. So instead, we'll sort of modify the follow the leader argument or modify the algorithm to use an idea called either dual averaging or basically a mirror, which is basically the same thing as mirror descent, to express the sort of follow the leader algorithm in terms of prefix sum queries on the data stream, and then we can use our standard algorithms for prefix sum to get a differentially private version. Okay, so why is it that it has low? So I claim that when everything's strongly convex, follow the leader itself is a good idea. It has very low regret, and the point is that so we know that it's wait, I wrote the wrong thing here. What we know is that its crystal ball regret is at most 0. What we want to argue is that its forward stability is bounded. Okay, so we want to just by if each of the little cost functions is h strongly convex, then at time t the cost function I'm minimizing, which is the sum of all of them, it's ht strongly convex, and so the difference between wt and wt plus 1 is L over ht by this stability lemma. And because my function is Lipschitz, because my cost functions are also Lipschitz, what I know is that the actual difference in the cost function is at most, it multiplies by at most L, so that's L squared over ht. And then if I add this up over time, so again, sorry, this should be stability. I don't know why I wrote CBR. If I just add up over all time steps how much I've paid, it's L squared over h times the harmonic series, and so that's about log of t. Okay, so we're done. And just one note is if the FIs are not strongly convex, turns out what you can do is just add in a small strongly convex function, and if you sort of do it just right, this will give you non-trivial, though weaker bounds. Okay, you'll get. I'm not going to discuss that. Okay, so this gives us a non-private algorithm. It also gives us a sensitivity analysis that I won't go through. Basically, that was what was used in the work of Jain, Kothari, and Thakurta. You need one more idea to get really good regret here, though. So the sort of just using Laplace noise and a straightforward sensitivity analysis will give you something like quadratic regret, and you can get a lot better by using this idea that this strongly convex function, you can always lower bound it by these quadratic terms, right? And so what you do is you actually run your algorithm, or you analyze your algorithm not with respect to the original cost functions, but with respect to some quadratic approximation to those cost functions. And what you'll do is at any given point v, you can develop this quadratic approximation. It's just, sort of basically like a Taylor expansion. You take the gradient times w of v, that's the linear component, and then this quadratic component. And what we get is that this function equals, so f tilde equals f at v. And in general, it's always a lower bound for f. And a key idea which comes from the online learning literature is that for any algorithm, instead of measuring regret with respect to the real cost functions, I can measure regret with respect to these approximations as long as I define them at the right places, as long as I define them at exactly the points I actually tried to predict. And this gives us, so instead of using the real cost function, I use this sort of proxy function. And it turns out that gives us an algorithm that has exactly the same regret behavior as the regular follow the leader algorithm, but it's going to be much easier to make it private. And the reason is that, well, so there are actually a couple of reasons why you might want to do this, I should mention. One is speed. It turns out that in many cases, this algorithm can be rewritten in a form that you can run much more quickly. So it can, for example, if you're using the L2 norm, you basically, this algorithm is equivalent to the usual online gradient descent, that algorithm I gave you at the beginning of the talk. And in other norms, you can do a similar derivation. But actually, the real reason I want to use this algorithm is because what it tells me is that the decisions I make at some later time in the algorithm, they depend on a very concise summary of what I've seen so far. So they depend only on the sum of the gradients. The only place the data comes into my function that I'm minimizing at each time step is via the sum of the gradients that I've observed so far. Okay? And so by putting it in that form, I managed to, you can add noise to those prefix sums, and you get a much better type of guarantee. And that's how you get this guarantee of the form d over epsilon times polylogarithmic in t. So that covers sort of these algorithms here and here. These algorithms out here, they follow by a different analysis, the first and the last. And since I'm out of time, I won't go through it in any detail. But the basic idea is really just what I said, that differential privacy already gives us some stability. And we can just use that stability to get a non-trivial regret bound. Unfortunately, in this case, what we get is epsilon delta privacy only. You don't get epsilon privacy. Epsilon zero privacy. I won't go through it, but it's very straightforward. All right, so I tried to give you a concise summary of how online learning algorithms can be, differentially private online learning algorithms can be defined, and designed rather. There are a number of open questions. So in general, the dependency on the dimension of these algorithms is quite poor. Okay, so there's an exception, which is this Kalai-Vampala follow the perturbed leader algorithm has logarithmic dependency on the dimension. But the others, because they're all based on noise addition, they basically incur a bad dependency on the dimension. I didn't go into the results in the Bandit setting, but so one thing I should mention is that in the full information setting, most of the algorithms I gave you, they nearly match the best non-private bounds. So up to a factor of about 1 over epsilon in general. Okay, or d over epsilon in some cases. And so you could, in principle, get much tighter bounds. In a Bandit setting, the gaps are quite a bit bigger. They're polynomially large. And the last question I'll throw out there, which I don't have a good answer to, is whether or not these techniques, in particular this sort of linearization idea, gives us any insight into Hart-Rothblum style private multiplicative weights algorithms. I tried thinking about this. I don't think it really gave anything new, but who knows? And then one other thing I'll mention is you can imagine stronger notions of privacy, such as pan-privacy, that was defined in a paper of Dwork et al. And
Sasha will talk about it in his.
And Sasha will talk about it. Okay, so one might hope that these would give us new pan-private algorithms. And I'm not sure. All right, I'll stop there. Thanks.
questions while Pramod sets up?
So I guess there's some recent work which sort of puts a lot of online learning into the framework of follow the regularized leader, but with a weird regularization function.
Right. So so I'm not sure exactly. So this is Sasha's. This is your laptop, right? Did you want that back? So if it's what I think you're talking about, it's in the Bandit setting.
No, this is Orabona. This is just a NIPS, just like last week. So
Yeah, then I don't know. I'm not sure which
I was just
paper.
wondering what you thought about regularized. I mean, follow the regularized leader.
Right. So actually, what I mean, we use that in this talk, although I didn't say it explicitly. So when you the way I said you go from deal with general non-strongly convex functions is you add a term to them that makes them strongly convex. That's a regularizer, and that gives you, if you choose your regularizer correctly, that gives you non-trivial regret bounds. Okay, and it doesn't hurt your privacy much. How to use the funky regularizers that come up in more recent work, I'm not sure. So this is a very simple regularization strategy. One can imagine there's room for much more sophisticated ones. Yeah, John?
I sort of feel like I can get most of these convergence results and maybe sharper ones in the local model.
So I'm not sure about, so in the Jane Kathari-Thakurta paper, they discuss using the local model. So one big difference is that there's a big difference whether or not you're looking at stochastic, like IID data, or worst case. Okay, so these algorithms have much better guarantees in the stochastic setting, although I can't like rattle them off the top of my head what they are. So if I had to guess off the top of my head, my guess is that the bounds you have in mind are for the stochastic model, but I'm not sure.
Somewhere halfway between adversarial and stochastic.
Okay. All right. Well, maybe yeah. So yeah. So separating the models would be interesting. Certainly, these algorithms are not, as presented, are not, local.
Yeah. I'm just kind of curious what the best we could hope for is. I just don't.
Right. I don't know.
I don't actually know.
Yeah. I don't know. Other questions, or should, I'll take the other questions offline. I'll let Pramod set up.